Okay, let us come to a concrete example. Here, we are asked to maximize the function, the objective function fxy equals x minus y squared, subject to three constraints. The first one is x squared plus y squared less than or equal to 4. And the other two, these two are non-negative constraints, okay? Non-negativity constraint. And then you're asked to do this optimization problem by the Kuhn-Tucker formulation. So part A. Firstly, write down the Lagrangian but in Kuhn-Tucker version. So L tilde equals to the objective function x minus y squared, the objective function, minus lambda times, okay, in this case, I've only one inequality constraint that are not non-negative constraint. So I just need to include this one. So I need to put down x squared plus y squared minus 4. So this is the Kuhn-Tucker Lagrangian. Okay, basically, it's done by ignoring all the non-negativity constraints. Part B. Write down all the first order condition in Kuhn-Tucker formulation. So Kuhn-Tucker first order condition come in, well, 4 aspects. Firstly, all the equalities come from complementary slackness. So you have x times the derivative of L tilde with respect to x, okay? So you will differentiate to obtain 1 minus lambda 2x. So what is this? This is L tilde differentiated with respect to x. And you want this to be 0. And then you do it for every single variable. So you have y times, okay, when you differentiate L with respect to y, you get minus 2y and minus lambda 2y equals 0. So this is L tilde y. Okay? And then you need to do it for lambda as well. But you know that when you do it for lambda, what you obtain is the usual complementary slackness, i.e. you want this expression to equal 0. Okay? So these are all the equalities. But how about inequalities? So, on one hand, you have negativeness of the derivative with respect to x, okay, and y. So, when you differentiate L with respect to x, actually we did here. So you have 1 minus lambda 2x, which is L differentiated with respect to x, should be less than or equal to 0. And then you have the same thing for L tilde y, which we computed here. Okay, you want this minus 2y minus lambda 2y less than or equal to 0. And then you have positiveness of the Lagrange multiplier. So positiveness of the Lagrange multiplier. But in this case, you have only one Lagrange multiplier, which is lambda. Rectangle equals 0. And finally, you have the given inequalities. Which are x squared plus y squared less than or equal to 4, x greater than or equal to 0, and y greater than or equal to 0. So these are all the first order conditions in Kuhn-Tucker formulations. Okay, part C. Solve all the solutions to this system of first order equation. So part C. Okay, let me draw a horizontal line to separate them. Okay, we have 3 equations here, 3 unknowns, 3 equations. So 1, 2, 3. How should I start? I'm going to start with our new friend. What is our new friend? Our new friend is non-negativeness of L tilde and with respect to the variable. For example, look at this one. Okay? Observation. Observation is because I know that 1 minus lambda times 2x is less than or equal to 0. Therefore, I know, okay, from here, I know that x and lambda cannot be 0. X is not 0, and lambda also is not 0. Why? Because if x is 0, if x is 0, then you get 1 minus 0 is less than 0. This is clearly a contradiction. Similarly, if lambda is 0, then again you will get 1 minus 0 is less than or equal to 0, obviously also is a nonsense. Therefore, x and lambda cannot be 0. Why is it good? Because once I know that lambda is not 0, from the third equation, if lambda is not 0, then the other guy has to be 0. So therefore, R3 implies x squared plus y squared has to equals to 4. Okay? And using the similar argument, because I know that x cannot be 0, though the other bracket has to be 0. So 1 minus lambda 2x equals 0. And then we use our usual trick, we try to turn x in terms of the Lagrange multiplier. So we can write x equals to 1 over 2 lambda. But what should I do next? The only equation that I haven't touched is here. The second equation. If you look at the second equation, okay? If you look at the second equation, it implies either y is 0 or the other bracket is 0. The other bracket is minus 2y minus lambda 2y equals 0. But if the other bracket is 0, then what is lambda? Then lambda equals to minus 1. Is it possible? No, because we know that in this case, the Lagrange multiplier has to be non-negative. So this is impossible. So if this is impossible, then y equals to 0 must be true. Okay, so y must equal to 0. If y equals 0, then by this equation, so by, let me call it star. So using star, we know that x has to be 2. You may say, oh, why not minus 2? Remember, we have non-negative constraint. Therefore, all the x and y has to be greater than or equal to 0. So x equal minus 2 is rejected. And then what is missing? I have x, I have y. So what is missing is lambda. But I know that, what is lambda? Well, according to this equation, lambda equals to 1 over 4. So let me use double star. So by double star, lambda equals 1 over 4. Hence, we obtain only one set of solution. So x, y, lambda equals to 2, and then 0, and 1 over 4. And this will give me the maximum value of the function. So what is the original function? The objective function is fxy equal x minus y squared. So average f20 equals to 2. So the maximum value equals to 2. Okay, so that is how we deal with optimization problem using Kuhn-Tucker formulation. The advantage of Kuhn-Tucker is that it turns out the number of equations you deal with is a lot less, okay, a lot less, because you have much less number of variables, and that is easier to deal with. In this case, well, you just take a few steps, then you arrive at the only solution to this system of equation.